Welcome everyone. So today we are going to discuss binomial distribution. We have already discussed, right? So we will revise that, and Possion distribution also. You know the basics. We will see some properties of Possion distribution. UPSC question we did it yesterday. We will see that uniform distribution, and we will say something about MGF, and we will do some PYQs. Fine. So now let's come to binomial distribution. Binomial distribution, you know what is binomial distribution? When you conduct Bernoulli's trial and time, you get binomial distribution. And what it says? Let's say you did you conducted an experiment in which there were n trials, and out of these n trials, you are looking for S success. So how you will call it? Probability of X success is given by NCX p to the power x into 1 minus p n minus x. Fine. Okay, this is also called PDF. Sorry, PMF. We will call it PMF, not PDF. This is a probability mass function because it is a discrete distribution. Fine. Now, then you saw its mean is what? Its mean was given by expected value of this was given by NP, and its variance. Variance means this thing. Variance of binomial distribution was given by n into p into 1 minus p. Okay. Derivation also we saw. We saw the UPSC question as well, regimen, right? And what we did in derivation? X. Let's say what I will do. We did this. Expected value of x is equal to summation of x is equal to 1 to n x into PMF. PMF is NCX p to the power x 1 minus p n minus x. Fine. And how you solved it? Using two require. One was the user identity. I will not solve it, but you know x and cx is equal to n minus 1 c x minus 1. This identity you will use, and then you will put x minus 1 is equal to y, and then what you will get? You will get the expected value of right? We have already done that. Any problem? Now this is fine. Now we will move to, and similarly you will calculate the variance. For to calculate variance, you first have to calculate EX square. EX square, how you will calculate? X is equal to 1 and x square and cx px 1 minus p and minus x. See, this thing EX square you already calculated. This is NP, right? This turned out to be NP. So second term you already know. So NP square you will put, but you have to calculate this thing. And here also again, what you will do? You will solve it using you will do some manipulation, algebraic manipulation, and you will get the. Here also you have to use the same identity. And then you only thing you have to do it 2 times. Fine. So this is your binomial distribution. Now UPSC question we have already seen on that. There was a question I think in 2017-18 as well. So 17 the question was like there were 20 questions given. You have to look for just show me the paper. Maybe I will see that. Can you? 2017. This is 2000. I think this question came in 2017 or 18. Let me see. I think 2017 this question came. 2017. No, this is normal distribution. What about 2016? Let me see. Was it in 2016? This is there. Okay, yes. This came in 2016. Okay, question number 1B. Let us do this question. 2016 1B PYQ. Okay, now this question can be done using both normal distribution as well as binomial. So what it says? It says a multiple choice quiz has 200 questions. Okay, there is a quiz and it has 200 questions. each with 4 possible answers. Question is clear? There, let's say there is a UPSC exam. There are 200 questions, and each question has 4 options, of which only one is correct. Of which only one is correct. What is the probability that sheer guesswork, that somebody is just involved in guesswork, will yield 25 to 30 correct answer for 80 of the 20 questions? What you are doing? What is they asking? What is the probability that the correct answers? Let us call correct answer is X. Okay, this is equal to 25 to 30, right? Okay, this thing you are looking for. And how many question you out of 200 question you attempted? 80 question. When you attempted 80 question, you are looking for this number of success. Forget every formula and everything. Just go to the basics. Let's say 80 questions are there. You do the guesswork. And what is the guesswork? And what is the probability of being correct in guesswork? Out of 4 choices, one is correct. So what you will say? Out of 4, you will mark 1 question correct in 4 attempts, right? So indirectly you can say that my probability of success would be 0.25. Okay, because out of 4, 1 question is correct. And how many? What is the n value here? 200 or 8? No. See, out of 80 you are choosing. See, 200 in this question like of a redundant information, right? Superfluous, not redundant, superfluous. Okay. So you're out of 80, you are looking for how many success? 25 to 30. So now you can do it by 2 methods. When you can apply normal distribution, or you can apply binomial as well. Binomial, it would be slightly lengthy, but what you will do, you will write it like probability of X being greater than 25. Okay, you must write it like this. 25 X less than 30, right? So this will be equal to probability of X is equal to 25 plus probability of X is equal to 26, like that probability of X is equal to 30. Any problem here? See, you consider all the cases. Now let me write just probability for 1 or 2. Tell me the what will the probability of X is equal to 25. Out of 80, you are looking for 25 success. 25 success. The probability of success would be P. P would be P of what? Oh, yes. P power 25 into 0.75, 1 minus 75. So 1.25. How much? This is 55, right? 80 minus 25 is 55. But okay. This is your this number. Similarly, you will write all the other numbers. Okay. Let me write the last one. 80 C 30 0.25 Q power 30 0.75 power 50, right? And you have the calculator, you will calculate it. But again, can you see this is lengthy method? But always remember, a question, there is a binomial approximation to normal, right? So a question can be done by binomial as well as normal. Okay? Normal, depending upon the parameters, like what is the value of, let's say if they ask this value, what is the probability of getting correct from 10 to X, let's say 70 question, then I would not like to do it with the binomial. So even then you can do. What you will do, you will 1 minus, you will not calculate this value for 60 values. What you will do, you will 1 minus first 10 values and 1 minus last 10 values. You will get the middle sum. Fine? Okay, now this is done. Now we will move to exponential distribution. What we said in exponential distribution, important thing where it is used, it is a discrete distribution, and you remember the kind of okay, before exponential let us do Possion distribution. Okay, okay, but normal, right? See, normal distribution, when we'll discuss that I will tell. Okay, I will just now when you will understood. But simple to just to answer your question, there is let's say mean is there, right? And this NP, you equate these two things. In normal, what you do, z is equal to x bar minus mu upon sigma, right? Here x bar you will replace it by, sorry, mu you will replace by np. Okay, suppose this is a random variable. So this population mean you will get from np. Okay. See, even in the your Possion distribution, you saw lambda is equal to np, right? And variance, standard deviation you will replace by n into p into 1 minus p, because you know n into p into 1 minus p is equal to variance. Fine. We saw that this is the variance. So what you are looking for is standard deviation. So you will simply replace it by this, because in binomial case you will know only n and p. Fine. Okay. Now, Possion distribution, please write down. Just first listen, right? Where it is used, it is a discrete probability distribution, and where it is used, let's say there is a port, and you are looking for within 15 minutes how many ships will arrive there, or there is a servicing center like a restaurant, right? They are delivering, you know, some burgers, and they will look for, okay, how many people are coming. Okay. See, Possion distribution is also connected with your when you study in operation management, like things like just in time, MRP. So it is related, but I do not want to go into that zone now. So you understand, within a time interval, you are looking for number of customers coming. That is given by your Possion distribution. Its PDF is given by, here lambda is given your average rate. Average rate means, let's say on average so many people are coming in this particular time interval, right? Lambda is clear. Now one more thing, there is a few assumptions. What is the one important assumption of Possion? That you assume that a particular time interval is divided into many small subintervals, and within one subinterval, the probability of occurring an event is constant, right? Fine. So the probability of occurrence on an event is constant for all subinterval. Do not say 1 or 2 or even half. Say constant. Second, there can be no more than one occurrence in each subinterval. There can be less than one, but cannot be more than one in each subinterval. Let's say there was a 15-minute time interval, and you have divided it to, let's say, thousands of subinterval, right? So within one subinterval, not more than one ship can come. So it might happen to come, for a ship to arrive in a subinterval, you might need 6-7 subinterval, right? Got it? Third assumption is occurrences are independent. Independent, you understand. In statistics, whenever you say independent, you will mean only this thing. Probability of A intersection B is equal to probability of A into probability of B. See, here it looks very simple. Okay, independent is just like this. A statistician and probability theorists have invested their, they have written 10-volume work on this formula, that analysis. Okay, what independence mean? And that day we saw, let's say when you toss a coin, then head and tail are not independent within that trial. They are dependent and they are mutually exclusive. But when you conduct an experiment, so the outcome of this trial is independent from this trial. Why? Let's say here you have head. So again, at this place, you can again have a head or tail with equal probability. So what happened in the last trial is immaterial. Got it? And now, given this background, how you will write the PDF of Possion distribution? E to the power minus lambda s upon x factorial, right? This is your fine. And we saw its expected value is what? Lambda, and its variance again lambda. Okay. This is the important characteristic. What we saw in exponential distribution? Mean is again lambda, but variance is lambda square. Fine. See, in binomial, when we said Px is equal to x is equal to mcx, px 1 minus p n minus x, what it means? It means out of n, you are looking for exactly x number of success. Let's say out of 10, you are looking for 4 success, then it is given by probability. Similarly, here, what it means, if out of, within a time interval, you are looking for exactly 2 people coming, 3 people coming, let x is equal to 2. So what it means, within that time subinterval, only 2 people are coming. Yes, if x is equal to 2, if x is equal to 3, it means 3 people are coming. Fine. Now, please write a question. Practice question. There is a computer center manager report that his computer experienced 3 computer failures in the last 100 days. So what is happening? 3 failures in 100 days. See, in UPSC, one thing is very, very important in examination scenario. You have to identify the question is from whether normal distribution, binomial or exponential. And how you develop this sensibility through practice. So in this question, you have to tell me the keywords through which, okay, I will just read the question and you have to tell how you will identify in examination. This question is from, let's say, Possion, binomial or whatever. He experienced 3 component failure during the last 10 days. Then first question is, this is the computer center and his computer, he observed there are 3 failures within that computer system in last 10 days. Fine? Last 100 days. Okay. First question, what is the probability of no failure in a given day? So first question is, what is the probability of no failure on a given day? Second, what is the probability of one or more component failure in a given day? Any probability of x being one or more. Third part is, what is the probability of at least 2 failure in a 3-day period? Okay. At least, see, this question is the probability of at least 2, right? But in 3-day period. Now let us, so what do you observe here? You say there are happening 3 failures in 100 days. Okay, in examination, let's say you get question like this. First you will think, okay, what is my syllabus? Binomial, exponential, Possion, from where it is. Then from the language you will say, okay, they are talking about 3 failures in 100 days. So they are talking about something like average rate. Okay. So it will come through practice. So here you will think, okay, this is something about average. Then you will go to the question part. They are saying probability of 0 failure within a given during a given day. So from here you will realize within a time interval they are asking what is the probability of occurring that event. There is a time interval, so immediately you will say this is a question from Possion distribution. Got it? Now it becomes very easy. Tell me, what is your lambda? 3 upon 100, right? That is the average rate. How you define lambda? Mean, and mean is your 3 upon 100. Any problem? And this gives you average rate on what duration? On 1 day, right? Let's say how many failure will occur on 1 day? That is 3 upon 100. Fine. So probability of x is equal to 0 would be, I will write it here only, e to the power minus 3 upon 100. 3 by 100, right? 3 by 100. 0. Very good. Upon x factorial, right? That is 0 factorial is 1. This is okay. Yes. here you have to calculate 1 minus what? 1 minus?
1 minus e power.
See, you are looking for x greater than 1, right? So you will minus 1 minus probability. You will get it, fine. Here, see, here is the catch. Now tell me, their average period is 3 days. Here you got lambda, see, there's lambda. Now your new lambda would be, I'm calling it lambda dash. That would be 3 of. No, why?
E power minus 3 by 100 of 3 by 100 all for 0 plus e power.
Here, first you have to change the lambda. Lambda earlier was the 3. See, now what they're asking, probability of x being greater than for on 3 days. This is very, very. See, when we calculated this thing on one day period, right? What he is asking, probability of x being greater than on a 3-day period, right? Now 3-day period is when you take 3-day period, here lambda which you got 3 upon 100 was for 1 day. So now you have to calculate the lambda for 3-day period, right? And then only you will apply. So this will be this type. Always very, very important question. Okay. See, here aspirants make mistake. Here your length of the period has changed. Earlier it was 1 day. So it was 3 upon 100. So let's say there are 3 failures in 100 days. So how many failure would be in 1 day? 3 upon 100, right? In 3 days, how many failure? 9 upon 100. So that is your new lambda. Given this new lambda, now you will put it. Now you will do this question. It is not 3 whole power. It is multiplication. It is multiplication. Okay, not whole power. Fine. Probability now you can calculate it, right? How you will calculate it? You will write it probability of 1 minus x is equal to 0 minus probability of x is equal to 1. You will subtract these two things, you will get this number. Fine? 1 minus this thing. Fine? Okay, now we will talk about, yeah, tell me.
Okay, that is
it is greater than 2, na? So you will subtract. So now we will talk about the Possion approximation to binomial distribution. Possion approximation to binomial distribution. Right? What you do here? Let's say simply you put lambda is equal to NP. This is the way you approximate. So what is your Possion formula? PMF is given by e to the power minus lambda x upon x factorial. So what you will do, e to the power NP x upon x factorial. Fine. And when you will do it, two conditions. When the p is approximating 0 and n is approaching infinity, then only you can apply Possion approximation to binomial distribution. See what you're doing. You have to conduct Possion approximation to binomial distribution. And what is the condition? Lambda is equal to NP. In Possion formula, Possion PMF formula, you put lambda is equal to NP. You got this thing. And when you will apply this, when the probability is approaching 0 and n is approaching infinity. Fine. Okay. Now, given this background, what? Huh. See, this is okay. In binomial distribution, what was the mean? NP. NP, right? You got this thing from binomial. Let's say there is a question like this in which they have given n and they have given p, right? And the p is your very small, approaching to 0, and n is your very, very large. Then in this case, you will approximate lambda with NP. That is called Possion distribution approximation to binomial. Find it?
Yes, sir.
Okay. Now, any problem?
No, sir.
Sure.
If we are getting p value is equal to 0 and n value is equal to infinity, we can find by Possion method. So we
Yes.
are going to check
Yes,
the
yes.
value.
When your p is approaching 0 and your n is approaching infinity.
If p is approaching minus infinity, I mean,
P-
okay.
What is p approaching minus infinity? N is
Okay, I got it.
p approaching 0 and approaching to infinity, right? When your number of observations are very large and your probability is very, very less. Let's say in examination you get probability like this 0.001 and your number of observations is, let's say, 1000. Then you will apply Possion approximation to binomial. There was a question from Possion that we discussed yesterday, right? That was very simple. So given this background, now let us move to moment generating function we yesterday talked about. Can you recall what is moment generating function?
Yes, sir.
Hmm.
In the moment generating function, we can't, the distribution is not even.
Distribution is not. Moment generating function will give you moments, right? Although we call it generating. Let's say you got a function, and how you define that? Mx t, right? And let's say it's a continuous case. Then e tx into PDF. This is your in the case of a continuous case, right? This is a case of continuous. This is called moment generating function. I will write it MGF. Although not directly asked in UPSC, but this application is useful, right? When you study hypothesis testing and all those things. And in the case of discrete, it is this is your in the case of discrete, okay? When it is discrete, what will you will get the value of this function, and let's say when you take the first differentiation, you get the value of first moment. That is your mean. When you take the second differentiation, you get the variance. Third differentiation, skewness. Fourth differentiation is kurtosis. So this way you can generate the moments. But there was an observation that even if you get these moments do not characterize a distribution. Let's say I got the, let's say I got EX first moment, second moment, and second moment is this variance. And this way I got all the n moments. Then even then I cannot say that these moments will characterize a unique distribution. What I will write? I will write this. We cannot claim that these moments will characterize. See this, now this is the language you have to use. Characterize a unique distribution. We cannot claim that these moments, right, will characterize a unique distribution. Fine. Why? And then we saw one example as well. What was that example? We saw two functions.
The functions are different,
but
their moments are equal.
The moments are equal, right? So what I will do, I will just write them in 2 minutes. But more important was that we said two conditions. That what were the two conditions? No, just a minute. Yes, if there were two conditions, if the random variables have bounded support, let's say this random variable have bounded support, and they approach to this approach to 0 in the neighborhood of MGF exists in the neighborhood of 0, and its MGF exist in the neighborhood of 0. Neighborhood of 0. So, but if these two conditions exist, then you can say that these movement will give me unique what? Unique distribution. Okay.
One is random alias bounded support.
Yes.
And then the distribution is equal.
Then yes. Then you characterize the unique distribution. Or second condition is your MGF of this random variable exists in the neighborhood of 0. Okay. Now this is fine. Okay. You remember this thing as well. What I will do, I will go to this one. D to the power and D Tn E Tx. Okay, we will just write it M X. Okay. Is equal to E X N. Yesterday we saw this thing, right? Any doubt on this?
No, sir.
E X M X P T0. Actually, you can write it. Actually, this is the notation of writing this. I will write exactly that notation. MX T is equal to 0. Okay. This is a notation. See, what it simply means, you are differentiating a moment function. Okay.
Yes, sir.
This is a moment, you are differentiating in n times. Okay. Here you are differentiating it n times, you will get an nth moment. Fine. Given this, so similarly, let's say you differentiated one time, you got the expected value, differentiated second time, you got the variance. Now you might say things like this, that let's say I differentiated 2 times. 2 mx t is equal to 0. So you will say I will get ex square, and this is not variance. See, I understand this is not variance, but using this function and the first moment, you can always calculate the variance. No? Here you will get ex square, and from the first differentiation, let's say you will get the mean, and using this one and mean, you can always calculate the variance. So this is the nth moment, but when you calculate the central moment, let's say when you calculate the central moment, you directly get the variance. I think central moment definition also you can write. Yes, sir. Please write the nth central moment of x. Central moment. Right now, the nth central moment of x, random variable. It's given by, let's say we are denoting it by n mu. How they define it? Okay, minus mu power n. See, logic is very simple. Only the notation is problem. What you are saying? What the meaning of central? This means you are taking the difference from the mean, right? This is a random variable.
X minus.
This is expected value of x minus mu. Mu is your population. Generally, how you define it? You say, okay. So this is your random variable. You are subtracting and you are taking that expected value n times, and this is the way you define n as central moment. Let's say in this case you want second moment. What is this? You indicate here second moment. You will write e x minus mu what 2. Now what is this? This formula is nothing but your variance. Fine. Here you are getting directly, but here you have to do manipulation. First you will get the second moment. From that you will subtract the first moment ka whole square. Fine. Chalo. Now this thing is done. Let's see what else. What else?
But in the normal step by step moment, we
Yes.
can get directly.
Yes. You remember the gamma MGF formula? What is the PDF of gamma? See, it's difficult to remember, because the function. Let's say somebody says, what is the formula of normal distribution? Z formula. You will immediately tell. But somebody says, what is the PDF of normal distribution? It's comes difficult to mind, right? Not with it. So, but you must, you must familiarize your mind to those PDFs as well. Let's say you're writing gamma PDF in let's say in next 5 months 10 times. It will automatically become part of your memory. So gamma, if you have to calculate gamma MGF, so we saw the expected value of is given by alpha beta, right? And the variance, what are the variance? Any idea? What are the variance of gamma distribution? I have to see, even I don't not remember. They have not also given. Maybe it is some complex function. But anyway, you will see. So this expected value is important, and its PDF. Its PDF is given by 1 upon tau alpha beta x to the power n minus 1 e. Let me see what was the exact formula. Minus x upon minus x by beta, and this is your alpha. Okay, this is your PDF. This is your PDF for gamma distribution. And how you will calculate expected value from here? Tell me.
Integral of minus infinity to expected value of MGF. Integral of minus infinity to
infinity. 0 to infinity, right? 0 to infinity, you will integrate it.
Yes, sir.
Okay, so that is fine. And you can calculate the moment as well.
Yes, sir.
Let's say somebody asks you how to calculate the moment of this function. So what you will do? You will take this function, right? I'm assuming I'm calling it, let's say, k. Okay, the function is k, and you will do etx and 0 to infinity. Fine. Here you have to put dx where k is equal to this function. Okay.
Yesterday I would like the minus infinity to infinity.
For moment, no, for moment maybe some.
Gamma MGF moment generating function. Yes, sir.
It is 0 to infinity. Just no problem. You can make the changes. It is 0 to infinity. Okay, 0 to infinity. This is fine. And you can write the result, because 1 minus 1 upon 1 minus beta t alpha is equal to 1 upon 1 minus beta t power alpha. And we will not go into all this. See, this integration thing is mechanistic. This is not even required for UPSC. For UPSC, you are required for, we must know results. But when you practice, let's say this integration. Variance, I have to check, what is the formula, maybe some complex formula. But see, what is my important point? In UPSC, they were asked gamma, but binomial exponential, Poisson, hypergeometric, they have asked. Okay. We will also cover negative binomial distribution. You understood this part?
Yes, sir.
We are not doing integration here. We have directly written the result. Okay. When you differentiate it one time, you will get this thing. You can try. Differentiation is easy. When you will differentiate this function, what would be? It will become alpha beta. Fine. Now, similarly, tell me. Let's say if you want to calculate the binomial MGF, how you will calculate? Mx t a to the power tx and the pmf, right? mcx p to the power x 1 minus p and minus x. Okay, this is what you have to do. And simply you will take the x is equal to 1 to n. This will be your summation, and when you do it, what value you will get? You can finally write the answer. It gives you p e to the power t plus 1 minus p to the power n. 1 minus p to the power n. This is your m. This is your value of, this is your MGF, moment generating function of binomial. Now what you will do, let's say you differentiate it one time, t, mxt. So tell me what result you should get. If you differentiate this function one time, what you p, np, right? That is mean. Wonderful. Let's say you differentiate it two times. mxt. What you should get? Into 1 minus p. So now you have seen three methods of calculating this. One method is, let's say, generating MGF. Second method we saw by summation, right? Using summation binomial series. Third was we using Bernoulli's, and we compare Bernoulli's and binomial, right? So you have seen three methods. Chalo, this is fine.
Binomial MGF method also we can calculate mean and variance.
It's the different method, right? Okay. So now your this thing is complete. This thing. Okay. We just now we saw that sometimes movement do not characterize the distribution. Okay, and then we can give an example. Let's say there are two functions, function 1 and function 2. If I prove, let's say, not movement. Let's say there is a, let's say, PDF. This is PDF. Okay, there are two PDF, and using this PDF I get some moment genetic function, and I prove that, and then I differentiate those MGFs and I get movements, and I prove that the movements of these two PDFs, these two functions do not give, although the movements might be same. Let's say here is a PDF and here is a PDF. Using this I will calculate the movement, MGF for this one as well as MGF for this one. Then I will differentiate the MGF1 and MGF2 n times, and I will get the n moments. So if I prove that their moments are same, but they do not characterize the unique distribution. These distributions are different. Their graphs are different. Then the contention we made half an hour before will be proved. Fine. So you can write those functions. First PDF is 1 upon 2 by pi. It's difficult to 1 upon. There are two PDFs. Okay. First PDF is given by 1 upon root 2 pi x into e to the power minus log x square upon 2. Don't worry, it is not easy to remember for humans, all the formula. But the logic you can always remember. What you can see, it's not, your mind will not never remember this formula. But what your mind will remember is this thing. Let's say I'm writing the second PDF as well. Second PDF is given by, just f1 x into 1 plus sine 2 pi, 1 plus sine 2 pi log x. Okay. This is the formula. Now what I'm saying, I will calculate the MGF of this. let's say I calculate the MGF of first function. How I will calculate? ETX and this one, right? F1x into dx. Similarly, I can calculate the MGF of 0 to infinity e to the power tx into f2x into dx. Fine. You will get the moment derivative function. Then you will differentiate it then n times. You will get the moments. Any problem? I am calling it ex1 ex2 square minus this is ex1. Okay, we will just keep it. We will not put subscript. Right. Okay. Similarly, for this one, I will get right ex square and ex whole square. Just to differentiate between these two, I will calling it first one. This is second one. Okay. Now you see it will happen. We cannot do all the integration and all those things here, but it will happen the moments of when you, let's say you differentiate this function first time, whatever function you get and you differentiate it one time, you will get the same expected value. So here what is happening, your expected value are same, but your function graph is different. Distribution is different. So moment cannot characterize a distribution. Fine. If you want to see the graph of as well, this function, for your convenience, I will draw that. What I will do. Moments are same, but the distribution are not same. Let me take this one. These are the graphs of these two. Okay. fx2 is this is f1x. This is f2x, and this is your f1x. This graph, f1x. So now you can see that the graphs are different. This means the distributions are different. Distribution are different. So what indirectly means, even if two functions, two MGF get the same moment, they do not characterize the distribution. When I use the phrase characterize the distribution, means they do not give you the same distribution. Fine. Now what you will write? What else? Let me see a PYQ. Probability, previous year's question. In recent year, this is the decision support system, aggregate plan distribution. Okay, here they have given a question on level of significance. Test score are different, but this we will discuss when we will these two hypothesis testing. At present, we cannot discuss. Let me see anything else. Okay, you try one question. You want to what you can do? We will start with now hypergeometric distribution. Hypergeometric distribution. New topic. New distribution. Hypergeometric distribution. Hypergeometric distribution. Hypergeometric, see, many questions of binomial can be solved by hypergeometric distribution as well. First, you understand the condition. binomial distribution condition you know very well. What you are doing, let's say you did n trials. You are looking for x number of success. In hypergeometric distribution, imagine a condition that there is a bag, okay, in which there are some red balls and some green balls, okay. I'm calling it red balls and green balls, and the number of red balls are m, and the n minus green are, this is m, this is n minus m, and total balls are n is equal to total balls. Setting is very clear. There is a bag in which there are some red balls, some green balls. Green balls are m, and the red balls are red balls are m, and the green balls are n minus m. Now, okay, and see, binomial distribution, there were two important assumptions. What? You can have only two outcomes, yes or no, true, false, like that. And each trial is independent, right? In each trial, the probabilities were independent. Here, what is your, see, very, very important assumption. Now you are withdrawing your balls from this, and you are withdrawing all at a time. When you do all at a time, it is replacement or without replacement? See, you are withdrawing at all at a time. So replace, where is the question of replacement? It is it is without replacement, right? You are withdrawing. Let's say there are 10 balls. I withdraw 3 all at a time. So there is no question of replacement at all, right? So write down that it is you write the withdrawal is without replacement. Withdrawal of x balls is all at a time or without replacement. Fine. Without replacement. This is important, this assumption. Then, what is the probability? Exactly x balls are red. Now this is what you calculate in MGF. Also in this I will write it here. Not probability of x is equal to x, and it is given by n c x. Okay, and m c x, and here it is n minus m, right? N minus c, n minus x. Let me check the formula once again. I'm writing it after a long period. M c x, n minus x, k minus x. Just a minute. Okay, sorry. You took okay, you withdrew 4 balls, k balls. Okay, but just a matter of notation. You are withdrawing k balls out of this pack. You withdrew k balls, and they are looking for probability that just it will be k minus x. Let me check once again. Yes, now it is fine. So what is the setting? You had this total number of balls. Red was m, green was n minus k. Out of these n balls, you withdrew how many balls? K balls, all at a time. Fine. And then you are looking for out of these k balls, how many are out of, what is the probability that out of k ball, x are red balls? What you are looking for? Probability of exactly x red balls out of k balls. Fine. Got it? So just to say it again, there is a bag in which there are n balls. In this there are red balls and green balls. Red balls are m, and the green balls would be m. Very simple. Now out of this bag, in which you have n balls, you are withdrawing how many k balls. So can you see? Now you understand this. What is your this thing denominator? Out of n, you are selecting k. Now what you are looking for is the k balls which you withdrew all at a time without replacement. How many balls are red? Because this bag has both red and k. So now what you are doing? You are in numerator. You are saying if my m balls are there, so I'm looking for x red ball. So this thing. So remaining ball would be what? Green. So n minus m. See, if out of m balls you have to select x balls which are red. So the remaining ball would be nothing but the k minus x. K minus x has to come from green balls. Fine. Okay. Now this is the. Now you can do one numerical on this. Okay. I want to see one numerical. Suppose just write a numerical on hypergeometric distribution. Suppose a retailer buys goods in lots, 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 and each item can be either acceptable or defective. Defective, that is, acceptable, the item is acceptable and it is defective. Okay. See, in OM, you will study capability index, CP, CPK. That time this understanding will be, will become more defined. Let n is equal to the number of items in the lot. N is equal to the number of items. Okay, the retailer bought n number of items. And K is defective. Sorry, M is defective. M is defective. Total items in a lot, and M is defective items. Defective items. Then we can calculate. No, n minus k would be acceptable. Na? See, if there are total n items, m is defective. So how many will be acceptable? N minus k? No. So can we calculate the probability that a sample of size k, calculate the probability that a sample of size k contains x defective items. Size k, so I will say probability of k sample containing x defective items. Now see, this question and this question is not very different. Here what you are having total n balls. In this question what you are ordering n items. Items could be defective or acceptable. Here you had red balls or green balls, only two types of balls. Total defective balls, total defective item there are m. Here your red balls are m. Now you took a sample of k. You are looking for how many are defective. This means here you took a sample of k. And
what we have to find? Defective.
What is the probability of out of the k, sample size k which you ordered, which you selected, x are defective. Okay. Here what you did, you took a sample size of k again. You look for how many of those balls are red. So your total sample size was n. Out of n you selected k, and you were interested in knowing out of these m balls how many. Out of these k balls how many are red. Same thing you will do it here. Now please write the values. Suppose, the lot size is 25, n is equal to 25, and the sample size is 10. I'm just writing in this question, n is equal to 25. Sample size which you would draw, this 10, and let's say you're looking for success. What is the value? What is the 6 defective? N is equal to 6. What is the probability of this event? Just a minute. And m is equal to 6. K is equal to m is equal to 6. They have given m is equal to 6. Okay, and okay, and there is no defective. You know what they are saying? What is the probability of this thing? That you see what they are saying. Now you understand the setting. The total 20 parts were there. Out of those, you took a sample of 10. Now what you are looking for? There is no defective at all. There is no defective. Tell me. You will apply the same formula. Probability of 0 is equal to, denominator is K. Right? It goes sample size. M, C, X, not K. Here K. So N minus M, C, K minus X. Fine. You simply have to now put the values. (25) this will be, this is nothing but the 25 C, 10, M is your 6, C 0, this is nothing but 19 C 6. This value you get, and let me answer 0.028. 0.028. See, in these questions, what you have to remember? See, this calculation is not very important. Anyone will do that. What is more important is understanding the setting. Once you understood this example, so whenever you will recall hypergeometry, you will tell yourself two things. That there is a sample size. In the sample size, there are only two outcomes. Whether it can be defective, non-defective, red, green, yes, no, there can be two outcomes like binomial distribution. Fine. Now, out of that sample, I am taking K. You will just withdraw K, and all of them at a time. At a time. That means without replacement. That is an important observation. Without replacement. Fine. Yes, when you take without replacement, and then you will calculate the probability of getting exactly X out of let's say red or defective, whatever it is. Fine. And you will write this formula. Now, see, this calculation and everything anyone can do. But whatever question you will get in examination, molding that question according to this formula, that is the key. And that comes through practice. Fine. Okay. So, let me see.
Sample spaces means how many times we are taking.
Yes, let's say you had n items. If you are taking k items out of that, this is okay, right? So you are.
The success must be
They might. Let's say you drew a sample of k size.
How many times we are taking that?
Not how many times. In one time, how many items you took out? You are taking out. See, let's say there is a bag. It contains 40 red balls and 60 green balls. 60 green balls. Okay. This is okay. This is your total is n is equal to 100.
Yes,
And you know m is equal to 40 and n minus m is equal to 60. Now when I say k, what I'm trying to say, let us I take k is equal to 20. So I withdraw a sample of 20. all at a time, or one at a time I am withdrawing for 20 balls. Out of those 20 balls, let's say I am asking how many balls are red. Sorry, what is the probability of 5 balls being red? Out of those 20 balls, k is equal to 20. I am asking what is the probability of x is equal to 5. Then just tell me. Now giving this understanding, tell me the formula. What will be the formula here?
P of x equal to 5.
Wonderful. Is equal to
MC 5 m is 40.
total quantity. How much? 100.
Then for that is 100.
Then
100 C 20.
20. Very good.
And then in numerator,
Huh.
40 C 5.
40 C5. Wonderful.
40 C 5.
Just a
And
minute. Just a minute. 40.
C 5.
Huh.
20 C 5.
20.
C 5.
Why you say 20?
N minus 0.
हाँ तो
Yes, direct.
what is n minus m?
60 minus 40.
See, n minus m. Your n,
Yes, sir. Yes, sir. Yes, sir.
n minus m is 60, right? 60 C what?
5. 20 minus 5.
20 minus 5. 15. Very good. Wonderful. Right?
Yes, sir.
This thing. Okay. Right. So what we will do? We will stop here, right? Today and in the next class, what we will discuss? We will talk about, let's say, we will do more PYQs. We will take important PYQs and then we will move into hypothesis testing.